Hey guys, welcome to the next video on OpenCV tutorial for beginners using Python. In this video, we will discuss about smoothing or blurring images in OpenCV. So smoothing, which is also known as blurring, is one of the most commonly used operation in image processing. The most common use of smoothing operation is to remove noise in the images. Now, when smoothing or blurring images, we can use diverse linear filters because linear filters are easy to achieve and are also relatively fast. Now, there are various kinds of filters available in OpenCV. For example, homogeneous, Gaussian, median or bilateral filters, which we will see one by one. So first of all, we will see the homogeneous filter. So homogeneous filter is the most simple filter, and in homogeneous filter, each output pixel is the mean of its kernel neighbors. Now in homogeneous filter, all pixels contribute with the equal weight, and that's why they are called homogeneous filters. Now those of you who don't know what the kernel is, I have explained about kernel in the last video, so you can see the last video. And in simple word, a kernel is a shape which we can apply or convolve over an image. And you can use, for example, NumPy to create this kind of squared kernel. So in homogeneous filter, the kernel looks like this image which you see on your screen. So in homogeneous filter, kernel k is equal to 1 by the width of the kernel multiplied by the height of the kernel. So let's say we want to use a kernel of 5 by 5, then using this formula we will have k is equal to 1 by 25, and then we will have our kernel matrix of 5 by 5 ones. So let's create this kernel first of all, and then we will see how to use this kernel for the image filtering using 2D convolution or homogeneous filter. So what I have right now here is the simple code which loads this image using matplotlib, and this code you might already know because I have explained in detail how matplotlib works and how to read the images using OpenCV. One thing to note here is I'm just converting the image from BGR to RGB because matplotlib reads the images in the RGB format and OpenCV reads the images in the BGR format. So this conversion is necessary. So let's define our kernel. So I'm going to just say kernel is equal to np dot ones, and then we are going to take the kernel of 5 by 5. So we are going to define this kernel 5 comma 5 of ones. So I'm going to just say np dot float 32 here, and then we are going to divide this kernel by 25 because our kernel is of 5 by 5, because the formula which we have seen, in that formula we have the kernel which was a matrix of ones, and then we have the multiplication of 1 divided by the width and height of the kernel. So that's why the multiplication of the width and height is 25. That's why I have taken 25 here. So now we have our kernel, so we can define our destination image using this kernel, and we are going to use cv2 dot, there is a method called filter 2D which we are going to use, which is used for this homogeneous filter. So here the first argument is the image, the second argument is the desired depth of the destination image. So for now we are going to take it as -1. The third argument is the kernel. So now when we have applied this kernel on our image using 2D filter, let's see what the output will look like. So I will name this image as 2D convolution, and the destination is the final image which we got using filter 2D. and let's increase this range by 2, and let's say we want to show this image on matplotlib in 1:2 format. Okay, so I'm going to just run this image. So this is the result. On the left hand side is the original image, and on the right hand side is the 2D filter applied image. So this is the image which we got by applying the homogeneous filter using filter 2D function. So you can see on the corners here there is a little bit noise, and after applying this 2D convolution over this image, you can see all the corners are now smoothened, and overall this image is now smoothened or blurred a little bit. So these noises are removed or suppressed by this blurring. So this is one way of blurring an image using filter 2D, right? Filter 2D function. Now, as in one-dimensional signals, images also can be filtered with various low-pass filters or high-pass filters, etc. So low-pass filter helps in removing the noise or blurring the image, etc. And high-pass filters helps in finding edges in the images. Now, when you want to achieve image blurring, we need to convolve over the image with the low pass filter kernel. Now, there are some algorithm. As I said, there are various kind of algorithm available in OpenCV. So we will also see them one by one. So first algorithm is the blur method, or it's also called the averaging. So what I'm going to do is I'm going to define a variable called blur, and then I'm going to call a method called cv.blur. Okay, so this is the method which we will use to apply averaging algorithm for blurring the image, and this takes two arguments. One is the image and second is the kernel. So the kernel we are going to apply is once again 5x5, and now we are going to just see the result of this blurring method. So we are going to just load it using the matplotlib. So range, I'm going to increase it by 1 once again, and let's see this these three images in 1:3 format on the matplotlib window. So this is the result, and you can see the original image, the result which we got using the filter 2D method, and the result we got using the blur method, which is also called averaging. So the result is more or less looks the same to me, because we have applied the same kind of kernel to both the functions. So this is the result of filter 2D function, and this is the result of the blur function. Now there are more functions which are available in OpenCV, so let's see them. So the next algorithm which we are going to see is the Gaussian filter algorithm. So the Gaussian filter is nothing but using different weight kernel in both x and y direction. So in the result, pixels located in the middle of the kernel have the higher weight or bigger weight, and the weights decreases with distance from the neighborhood center. So pixels located on the side have smaller weight, and the pixels located on the center have the higher weight. So when we take a 5x5 kernel, its result is going to look like this, which is shown in the image. And now let's see how we can use this Gaussian blur in our OpenCV code. So I'm going to remove this semicolon which I somehow added here, and let's declare a variable called g_blur for Gaussian blur, and then we are going to use cv.GaussianBlur. So the method name is Gaussian blur, and the argument here are same as the blur method. So first argument is the image itself, second argument is our kernel. We are going to take the same kernel of 5x5, And the third argument here is the sigma x value, which we are going to take 0 for now. And let's see the result of the Gaussian blur method when it's applied to an image. So I'm going to just define one more title, which is G-blur or Gaussian blur, or let's take this name, which will be more clear. And then our result image is G-blur, and let's increase the range to 4, and let's say we want to show this image in 2 by 2 format, so 2 rows and 2 columns. So I'm going to run this code, and for OpenCV logo, the results looks the same. You can see for the 2D convolution or filter 2D method or blur method, using the Gaussian blur, you can see there is a little bit different between the blur method and Gaussian blur method results. The Gaussian blur result is more better in my eyes than the blur method. Let's try this Gaussian blur method with another image. So I have this image called halftone underscore Gaussian underscore blur, and I'm going to run this code now with the new image, and you can see the result now. So this was the original image, which have too much noise here. So you can see the pixels here which have too much noise, and after applying the Gaussian blur, you can see this eye image in a much better way, and all the noise is removed. So the Gaussian blur method is designed specifically for removing the high frequency noise from the image, like this one. Now let's see the next method, which is called the median filter. So median filter is something that replaces each pixel value with the median of its neighboring pixel. So this method is great when dealing with something which is called salt and pepper noise. Now if you don't know what the salt and pepper noise is, you can open the Wikipedia and under this URL, or just search for salt and pepper noise Wikipedia page, and you can see more details about salt and pepper noise. So you can see this is an image, and there are some pixels which are distorted here. So there are some pixels where the white dots are there, or white noise is there, and there are some places where the black noise is there. So that's why it's called salt and pepper, because we have white pixels which are distorted like salt, and we have the black pixels which are which looks like pepper. So that's why it's called salt and pepper noise. So I have this same image which I'm going to use as a source now. So it's called water.png in my case. And now let's see how we can use the median blur method. So I'm going to just define a new variable called median, and then I'm going to use cv.medianBlur method. So this method is called medianBlur, where the first argument is the image and the second argument here is the kernel size. Now one thing to note here is that the kernel size must be odd here. So this must be a 3 or 5 or 7 and so on, except 1. Okay, so when you just give 1, it's going to show you the original image, and let's say we just give 3 here as the kernel size, or in our case we have the kernel size of 5, so let's take the 5 kernel size here. So let's just show this result of the median filter in the matplotlib window. So I'm going to just increase the range 5, and let's say this is 2 by 3 matrix now, and I'm going to run this code, and now you can see the results of all the filtering method, and you can see the best result you get using the median filter method. So when you have this kind of salt and pepper dots on your images, then you can use the median filter. Now let's see the last filter, which is called the bilateral filter. So by using all these filters, for example, homogeneous filter or averaging or the Gaussian or the median filter, we not only dissolve the noise, but we also smooth the edges. And sometimes we need to preserve the edges. That means we need that all the edges must remain sharper even if the image is blurred. So let me show you one example. So I have this lena.png image. So I'm going to define a variable called bilateral filter, and then there is a method called cv.bilateralFilter, and this bilateral filter takes the first argument, which is the image. The second argument is the diameter of each pixel neighborhood that is used during the filter. So let's take it as a 9. The third argument is the sigma color, and the fourth argument is the sigma space. So the sigma color is the filter sigma in the color space, and sigma space is the filter sigma in the coordinate space. So for this, we are going to take this filter sigma color and sigma space as 75 and 75 here, and let's see it in the result window. So bilateral filter, and then the result bilateral filter, and this gives me error because this image is called lena.jpg, not png, so jpg, and then we need to increase this range by 1 to see all the 6 images. And let's run this code and let's see what happens. So you can see the result now. So let me make it a little bit bigger so you can see them, and from here also. So now you can see by applying the bilateral filter, the edges are preserved in a much better way. So here you can see the hat border is blurred, but here you can see in the result the border of the hat are preserved. So the images in which you need to preserve the borders, then you can use the bilateral filter. So bilateral filter is highly effective in noise removal while keeping the edge sharp. So these are some of the methods and algorithms you can use to smoothen or blur your images using OpenCV. I hope you've enjoyed this video, and I will see you in the next video.